Okay, welcome back. Here we are with this is an exciting day. This is the last lecture of chapter 1. Woohoo! We are going to move to chapter 2 very soon, this week, right? So here is our final topic of chapter 1. We're going to look at the logistic equation in a little more detail. A particular autonomous first order ODE, right? What do we know here? We could write the x dt as x prime. I wrote it out to explicitly show the independent variable is t, the dependent variable is x of t is our unknown function. It generally describes some type of population, and the rate of change of that population is proportional to the product of the number that you've got at some time t and this quantity, m minus x. So one of the things we're going to explore a little bit is what m is, and k is our constant of proportionality. Okay, so let's think about the first thing we want to talk about with this idea related to phase diagrams and phase planes, phase portraits. So let's talk about the equilibrium. My goodness, I thought I had turned that off, but apparently not. The equilibrium solutions. That doesn't look so good. The equilibrium solutions. What are equilibrium solutions for this differential equation? Well, solutions x, our dependent variable, equal a constant. Therefore, dx dt is 0. So it's already written as a nice product there. It's not too hard to see. There's two equilibrium solutions. What are they? Good. The only way k times x is going to be equal to 0 for k some positive constant is if x is 0, right? And what is the other equilibrium solution? Very nice. M minus x is 0, right? When x is equal to m. Again, m is a positive constant. So we have two equilibrium solutions. They have these equations. If we're going to think about the phase diagram, then we're going to have two critical points. Right? What are our two critical points? We're going to draw right here. This is our x-axis, right? And our two critical points are going to be x equal to m and x equal to 0. Okay? So these are our two critical points. Yeah? Okay, so now let's just think about this particular equation. What do we know? We know that this constant is positive, right? And so if I try to think about a sign chart for x prime, sign chart for x prime, and I draw this, and this is x. So now I'm drawing x horizontally, right? Just because I like my sign charts kind of that way. But I know x is really my vertical axis because x is my dependent variable, right? So where can we split up this x-axis? It's at 0 and m, okay? Now when we're talking about population, something physical like that, x being negative doesn't make a whole lot of sense, but just for fun, just in case, let's just analyze it in general for all possible x, okay? Whereas in the context of a number of people in a population, negative might not be so good, right? So let's look at this expression, okay? It's a product of two things. This guy's always positive, so it's not going to change the sign of x prime dx dt, and that's where the sign of x prime is going to tell us when x is increasing or decreasing, right? So let's think about it. If I am a number, say between 0 and m for x, right? So then if I'm between 0 and m, let's just go there first, then that means x is positive, so this guy is positive. And if I'm smaller than m, right, if I'm a number x that's smaller than m, and I'm going to take m minus a number in here, then that's going to also be a positive quantity. So this will be positive times positive for any x between 0 and m, and that will give me positive here, yes? All right, suppose I'm the number x bigger than m, right? Well, then I'm positive, so this guy is positive if I put in an x here, and then if I put in a number for x bigger than m, then m minus something bigger than it is going to be negative. So it's going to be positive times negative is negative, yes? And what if we put in an x smaller than 0, right? A negative x. Then this guy is negative, and then minus a negative x, that would make this positive, so this whole term would be positive. So it would be negative times positive is negative. So there's our sign chart for x prime, right? So what does that mean, right? That means that, right, x is decreasing for x less than 0 or x greater than m, and x is increasing for 0 less than x less than m, right? We know that about the graph of x. Now, we aren't going to draw just yet the representative solutions. We're just going to see how, like, okay, well, let's just do it from our phase diagram and kind of see what's happening. So what happens? What does this mean? Well, if I am above m, then solutions are decreasing, right? If x is above m, solutions are decreasing. If x is below m, between 0 and m, then solutions are increasing, right? What type of critical point is this guy right now? So just having done that, what can you tell me about the critical point m? We have arrows like this in our phase diagram, so therefore, if we start away, we go toward. If we start away, we go toward. So this is a asymptotically stable, right? Stable critical point. Yeah, that's what m is, okay? Now, let's look at 0, the other critical point, right? So if I'm above 0, right, what is happening? Solutions go away, right? Solutions are increasing. And if I'm below 0, solutions are decreasing. Solutions go down, right? So tell me about this critical point. Whoops, I think I just ruined this red marker too. This critical point is if I'm a little bit away, if I'm right at 0, I stay at 0. If I'm a little bit away from 0, what do? I move away from 0. And if I'm a little bit below 0, I move away. So what type of critical point is this? It's kind of purpley now. An unstable critical point. It doesn't seem like it was a very good red marker to begin with anyway. All right, makes sense, right? So we got that just straight up from the diagram. I mean, we just did that. That was pretty quick and easy, yeah? Pretty quick and easy. Okay, so let's take a look at how that would translate then into our graph of representative solutions, right? This is x versus t, right? So what do we have, right? We've got a critical point at x equals 0, or sorry, an equilibrium solution. An equilibrium solution at x equals 0, so that's our horizontal line, right? X equals 0, and then we have an equilibrium solution at x equals m, right? The horizontal line, x equals m. And they split the plane into 3 regions, the equilibrium solution, here, here, and here, right? So now we have 3 regions where we want to put in the behavior. Well, so what's happening here? Without even going through the effort of taking the second derivative and looking at where concavity changes, we can kind of see just straight up from this what's really going to happen over there, okay? So let's think about what's happening. So if I'm above m, right? If x is above m, solutions are decreasing, right? Solutions are decreasing. If I'm going to approach m asymptotically stably from above, then if solutions are decreasing, they're gonna have to be decreasing in concave up. You should be able to show that they are, but they're gonna have to be, okay? There's no other way. This wouldn't work. You would cross the decreasing and concave down, you would cross the equilibrium solution. You can't do that, okay? Not for a problem that is nice. By Picard's theorem, you should guarantee you should help yourself understand why that would be nice. Okay, what if we're down here? Let's look below 0, right? What happens? Solutions are decreasing, right? Solutions are decreasing, okay? So this guy is unstable, right? We're moving away from 0 as we are, and as t goes on. And so what is happening, right? Solutions are decreasing. You should be able to convince yourself that solutions here are concave down and decreasing, okay? Again, concave up and decreasing wouldn't work down there. Maybe you can see why. What happens in between these two guys, right? Solutions are increasing, right? Solutions are increasing. Well, so could they possibly be always increasing in concave up? Well, no, right? It would cause us to cross this equilibrium solution. That doesn't make it, you can't do that, right? If things are nice, and they are here. And so could it be fully increasing in concave down then? Well, no, because that would mean we would cross the equilibrium solution here, right? And that's not going to happen either. So solutions have to be increasing, and there must be a change of concavity in here, okay? And so it's not too hard to show, and we'll talk about this in just a sec, and this might look a little familiar, that solutions are going to be increasing and concave up, and then change to increasing concave down, okay? And that's kind of, whoops, they're not going to cross that guy. Right? Because he's an equilibrium solution. Yeah, right? Okay, and a solution cannot be crossed. All right, therefore, you get this? You get a sense of what's happening here? And you see, as time goes on, right, what happens? Solutions get closer and closer and closer to this M. What is M? M ends up being the carrying capacity for the population. The carrying capacity for the population, right? It's our asymptotically stable critical point. If we start out with more numbers than M, what's going to happen? You're going to decrease as time goes on. You're going to end up with a population of M, right? If you start out with a positive number, right, in a realistic problem, then you're going to do what? You're going to increase, but then you're going to taper off until you approach M at your carrying capacity, your total number of population, okay? This idea, right, is used in all kinds of different modeling, right? Whether it's populations given a limited resource, whether it's disease modeling, the number of sick people in a epidemic, might sound familiar. It's also the same idea of number of people who have heard a rumor, number of people who've, seen some Insta gone viral, right? There is some carrying capacity in those situations, and it's all kind of a very similar idea, okay? Lots of different applications for the same model, right? Spread of a pollutant, right? Or a perfume through the air. So let's look at this slightly more carefully as well and see what also happens in a problem like this. So hopefully you should be able to see that concavity changes from doing the type of analysis that we did when we started talking about slope fields and looking at more in-depth ideas related to concavity. So let's take a quick look at this problem as well. Before I erase this, this was quick and easy, right? faster than doing all of that stuff that we were doing back on the last quiz, right? That's kind of nice. Again, you can only do that when you've got a nice autonomous differential equation, okay? This guy is a little more complicated when you got your independent variable involved. So these little diagrams are super nice because they're quick and fast. Let's look at when you have the change in concavity, right? So the idea of an epidemic or what, a lot of different things that you're kind of worried about when you have the growth is, well, when is the exponential portion of the growth, when are things going to kind of turn around, right? When is the rate of change going to stop increasing and start decreasing, yeah? When do I switch from concave up to concave down, right? You want to flatten the curve, right? Have you heard that say lately, anywhere, ever, recent? I don't know. We want to flatten the curve, right? And the curve starts to flatten at an inflection point, right? Okay, the curve is increasing and then starts to flatten and begins the flattening process at the inflection point. So finding where those inflection points occur are pretty important. And here it's actually easier. So if I just rewrite this as x prime, and this time I will just multiply through just for fun, just to see it again, k, and I'll put the m out in front, kmx, right, minus kx squared, right? That's that same equation. Another way to write that same equation. It's generally often written like this for a variety of reasons, right? This is the way you want it written if you're going to solve it. We'll do that in just a sec as well. This is also nice, the way you want it written when you're going to do any of this type of analysis, because it's already nicely factored for you to think about your sign charts, right? Okay. But let's look at this. Let's take the second derivative, right? X double prime, if we're going to think about concavity, right? Okay, so that's our question now, concavity. It's actually a little bit simpler to take the second derivative if we write it like this than this, because here we have to use a product rule, right? Product of two functions. And we're taking this derivative. Prime means with derivative with respect to t, right? So don't forget that x is itself implicitly a function of t. It's implied that x depends on t, right? That's the whole point, right? That's what we're looking at. X as a function of t. So I'm going to take the second derivative, then k and m are constants, so they are multiplying constants from the constant multiple rule. And then I'm going to take the derivative of x with respect to t, that's just x prime, right? And my difference rule, minus k is a multiplying constant, k times what is the derivative of x squared with respect to t? Good, times 2x times x prime, right? Implicit differentiation. Okay, good. So now what? Well, let's see, we've got this factor of x prime. Let's pull that out. So we have k times m, right? Minus, well, 2 I'm going to write in front, 2kx. Yeah, I just pulled out an x prime. Remember, if we're talking about concavity and where concavity can change, it's where x double prime is 0, right? Or doesn't exist. And here we already have pulled out a factor of x prime, and we know where x prime is 0 already, 0 and m, right? But that's where solutions take on different forms, and so you're not going to have concavity change there. So what does that leave us? It leaves us with this. Well, we can still pull out k, so let's do that. K, x prime, m minus 2x. And this is actually a pretty cool little result. Really, it's a logistic equation, right? So what do we know, right? This k is positive, so that doesn't change sign. We already talked about where x prime being 0 wasn't going to give us anything related to concavity. And so this guy being 0 is going to be the only place where concavity can change. And so what does that mean, right? M is 2x, or don't forget what letter you're solving for. Okay, good. X is m divided by 2, right? 1/2 m, okay? So at 1/2, in this model, right, we had these two equilibrium points, 0, no population, M, carrying capacity, right, maximum sustainable population. And what happens, the change in concavity is going to happen at 1/2 that distance, right, okay? So that's when things are going to turn, when the population reaches half of the max, that's when this model predicts the turnaround point, the beginning of the flattening of the curve. Okay, so that's kind of cool and fun, and then you can just test relatively simply here then what the concavity change will be, okay? In fact, let's just look at a sign chart for x double prime now, right? Just for fun. Maybe you can't see that green. So where can x double prime be 0? Well, wherever x prime is 0, which is 0 and m, and at 1/2 m, right? And so if I'm going to look at a sign chart for x double prime, then, and this is x, right? But this is a sign chart for x double prime. Okay, x prime plays into the picture, so let me think about being bigger than m again. If x is bigger than m, x prime is negative, so this guy would be negative. And if x is bigger than m, then m minus 2 times something bigger than it is going to be negative, and negative times negative is positive, right? Okay, nice. What if x is down here less than 0, just to simplify, right? If x is less than 0, what do we know? Then we know that x prime is negative there, so this guy is negative. If x is negative, negative times a negative is a positive, so negative times positive is negative, right? Okay? Now, let's look at here, if x is positive, but smaller than 1/2 m, right? Well, if x is positive, then we know x prime is positive from this sign chart, right? So that guy's positive. And if x is a number smaller than 1/2 m, then this piece is positive, right? Okay? And so we have positive times positive, which is positive. And then between 1/2 m and m, x prime is still positive, yeah? And so this guy is positive, but if x is a number between 1/2 m and m, then this guy is going to be negative, so positive times negative is negative. So what do I know about x? X is concave down here, x is concave up, x is concave down, and x is concave up, right? Let's see if that matches. Here, x is negative, and x is concave down, right? From here to here, x is positive, right? But smaller than 1/2, and x is concave up, yeah? We have an inflection point, you know, with not a precise drawing, but if x is between 1/2 m and m, then x is concave down, right? In this region, we have concave down functions, and above m, x above m, concave up. That's exactly what we expected, yeah? So there's a couple of homework problems, very similar, one of which talks about a disease spreading through the country, right? Which the infection rate is proportional to the product of already infected people X and the number of susceptible S, but uninfected people, right? Susceptible but uninfected, yes? That's minus X. Okay, so what else should we do with this model before we call chapter 1 a part of the history books for us? Let's have fun with solving it. I think maybe some more practice with integration skills will kill you. I don't know, just a guess. There's a lot of different types of integration that come up in our section, in our separable and linear differential equations and exact differential equations. And so, anyway, good practice. Make sure you are remembering all those different methods and how to deal with them. Okay, so before I erase this, remember, if x is positive, right, which we knew from our phase diagram, our simple little diagram, that's 1.6 type problems, that if x was positive, that the limit as x goes to t, as t goes to infinity, of x is m, right? Okay? That long-term m is our asymptotically stable critical point if you start positive, either up here or here. That's where you go, right? So our solution should also give us that information, but it's pretty cool. We had that information from our little diagram without, you know, that diagram we did, or one that was right here, that took us like 3 minutes, right? Okay, all right, let's solve this guy, okay? All right, so this is also a separable ODE, right? So let's solve. Yeah? All right, what do we do to solve this? Okay, well, we got to write it in separable form. Now, there's a variety of things we could do. We got to get all the x stuff on one side. We got to get all the t stuff on one side, right? Often when we have a constant k, it's always just simply nicer to leave the constant on this side, okay? So if I get the other x stuff, x times m minus x over here, right? And then leave the k there with the dt for something to integrate, that just makes it simpler, okay? So this is derivative form, this is differential form, ready for a separable integration, yeah? So my next step, I'll just use another color. Say, okay, now we can integrate these guys. Okay, well this side's super easy, right? What is the integral of a constant k with respect to t? Good. kt plus c. Yeah? Right? Okay. So, now the question is, what is this? So let's do that over here. What method of integration do we have to use in order to do that integral? I heard it. Partial fractions, right? So what do? Well, the idea of partial fractions is that this fraction right here, 1 over x times m minus x, can be written in its parts, the fraction parts that make it up, as some constant over x plus some other constant over m minus x, right? That's the whole goal. That's the whole deal with partial fractions. Now we can determine the a's and b's. We'll do that maybe a little bit later. But we don't even need to know the a's and b's in order to do this integral, right? So these two things are very easy to integrate as integrands versus that guy. So this is the same as the integral of a over x, right? Because this over dx over that is the same as 1 over that dx, right? So this is a over x plus b over m minus x. These letters might be freaking you out, but as long as you know what each letter means, you're good to go. Dx, right? A is a constant, right? So this is equivalent to a times the integral of 1 over x dx, yes? Plus, b is a constant, right? B times the integral of 1 over m minus x dx, yeah? Okay, this is our favorite integral now, right? What is the, so we have the constant a multiplying, what's the integral of 1 over x dx? I heard half of you say it correctly and the other half not. A times the natural log of, good, the absolute value of x. Now, again, for a population problem, x is positive in general, but we're just going to solve this guy in general in case we have some other type of model where, you know, negative people doesn't not make sense. All right, anyways, let's keep going. All right, plus what? Well, what is the integral of 1 over m minus x dx? Do the u substitution, right, and see that you're going to get a negative, right? Because u would be m minus x, du would be minus x dx, right? So dx would be minus du. So minus b times the natural log of the absolute value of m minus x, right? Now we're not going to put a plus c on the end of that because we already put a plus c on the end of this. We're just doing this side, right? All we need is 1. Okay, so we have our expression, yeah? Well, what are the a's and b's? Okay. So we did the integration without even knowing the a and b. That's pretty awesome, pretty cool, right? Okay. Well, how do you find the a and b? Okay, well, you recreate the common denominator, right? This is undo the common denominator, redo the common denominator. So it's a little partial fraction decomposition. Refresher. So I have this guy. I broke it down into these two parts, the fractional parts that would go together to make this common denominator. So if I redo the common denominator, I need to multiply this guy by m minus x over m minus x, right? So I'm going to have an a times m minus x plus this one would have to be multiplied by x over x. So plus b times x all over the common denominator of x times n minus x. I skipped a little step there. I hope you understand and see where that came from, right? And then what does that mean? This fraction is equal to that fraction. They have the same denominator, okay? What's the way we the simplest way we do this in calc? We just say, okay, well, the denominators are the same, the numerators got to be the same, and then we plug in some easy values of x. Right, so what's one easy value of x into this guy? If we evaluate it at x equals 0, right, that's an easy value, yeah? Then what would that say? The left-hand side is 1, the right-hand side is a times m, right? Yeah, because it'd be b times 0. What are we solving for? Oh yeah, a and b. M is a parameter in our problem, right? So there's no confusion. What is a? 1 over m. Very nice. Yeah? Now, what's the other place we want to evaluate this guy? What's another nice place to evaluate this expression right here? Yep, when x equals m, right? Because that guy's going to go away. So what's the left-hand side when x is m? It's 1. What happens when we plug an m in here for x? 0, right? Plus, there we go. What are we solving for? B, therefore B is also 1 over m, yeah? Okay, we good? So what are A and B? Well, 1 over m and 1 over m, yes? Awesome. Well, now some nice natural log algebra should be just like jumping out at you. You're just almost falling off your seat or out of your bed or off your couch, wherever you're watching lectures, with your notebook, writing down, taking nice notes. There's a lot of things we could do with this expression, right? Okay? A lot of things we could do with this expression. So one of them is that we could, well, maybe just factor out a 1 over m, yeah? And we have a natural log of the absolute value of x minus the natural log of the absolute value of m minus x, right? And what else? Okay. What are we doing? This is with a view toward what goes in here, right? We just did that integration, and it goes in here, and then we're going to try to see if we can manipulate an explicit solution, right? That would be plugging that in right here would be implicit solution. Yeah? We're going to see if we can manipulate out an explicit solution, and I'm specifically doing this because it looked like we might have some issues with some natural log rules, remembering some of those. So this isn't such a bad thing to do. All right, so now I've got my 1 over m here. What rule is this screaming out at you from natural log? Natural log of a minus natural log of b. Good. Natural log of a divided by b. Yes? Excellent. Okay. Okay. Here's another rule, right? I could at this stage take this 1 over m in, well, not just quite yet. Let's write this like this. 1 over m times the natural log absolute value of a over the absolute value of b is the same as the absolute value of a over b, right? So that's the same thing. I could take this 1 over m and put it up there if I wanted, right? Recall, right, the natural log. So what I have there is a times the natural log of b is the natural log of b raised to the a, right? I could do that with the 1 over m in the a spot, yeah? But I don't want to do that right now. And let's see why, okay? So this guy is very useful for some of your other work in linear differential equations. Hopefully you've discovered or rediscovered that nice little rule. Remember what we were doing? We were solving this integral. So now we're down to here. So now I'm going to plot that in for that. So there's a lot of different things we could have put. All of these things are equivalent, right? Any one of these we could have put in there, but I'm going to put this one in here right now. So 1 over m, this integral can be written as this. Why is that better? Well, first, there's only one natural log, right? And you still might be saying, well, why aren't you just going to put the 1 over m up here so you can e both sides, right? You're kind of getting to there where that's what we want to do, e both sides. But kind of for the same reason we left the k out here in integrated, it's just kind of simpler if instead of bringing this 1 over m up and dealing with this mth root, we just multiply through by m, right? Wouldn't that be nice, right? And now we have this equation. Now you can't multiply through here by m because you don't have an equation, right? That would just be totally wrong. But since we're saying this is equal to this, now we have an equation. This is equal to this, so now I can multiply through by m, and that gives me the natural log of the absolute value of x over m minus x is equal to mkt plus, should I write m times c here? Should I write m times c? I mean, I could, but m is a specific constant parameter, right? C is an arbitrary constant. An arbitrary constant times a constant is still an arbitrary constant. So we'll still just write c, yeah? Okay? Now, if I was multiplying by x, I can't do that, right? Because x would be a variable, or if I was multiplying by t, I couldn't do that because t would be a variable, and an arbitrary constant times a variable is not an arbitrary constant, right? But an arbitrary constant times the specific constant is still an arbitrary constant, yes? All right, good, we're getting better at this. That's all part of differential equations. Now what should I do? Woohoo, we're good. E both sides, right? Okay, good. Exponentiate both sides, so what do we do when we get that? Right, I'll just do e to that and e to all of that, right? All of it, right? Okay. So you can't just leave the plus c out on the end, okay? You can't just do this part and leave plus c, that's wrong, right? What you do to one side, you gotta do to the other side, the whole thing. And that's true with other expressions that you may have seen in your homework as well. Okay, so here we go. So the beautiful thing of this, right, is that we get our absolute value of x over m minus x comes out, right? We at least get rid of the natural log. And what do we have here? E to the mkt, rules of exponents. Good, times e to the c is what we get out of that. Now we've done this 1,000 times. It seems like 1,000, right? Not really 1,000. But what do we want to do now, right? This side is positive, that side is positive, right? If we want to account for allowing for the fact that what's inside could be positive or negative and legitimately get rid of the absolute values, then we replace this guy with some other constant c, which could be positive or negative, and that takes care of it. Now we still have an implicit solution for x, right? It's still an implicit solution. This is a lot of effort, right? A lot of work, yeah, to go through solving for what, right? For an explicit solution, you want to solve for x to get an explicit solution. So there's lots of different ways, lots of different implicit solutions. This is one, that is one. Taking this guy and having put it over there, and all of those would have been implicit solutions. All right, so let's keep going. Okay, what to do? All right, so let's multiply by m minus x. X is m minus x times c e to the m k t. Yeah. We want to solve for x, right? So now what can we do? Well, let's be a little careful here. We'll just make sure you see this cm e to the m k t, right? Minus cx e to the m k t, yes? Okay. We're gonna just leave this here just so that we don't make any mistakes, okay? Because you certainly can't replace that guy with something arbitrary, okay? So we're gonna bring this guy over. X plus cx e to the m k t. Did I write x? It looks like an x, doesn't it? Kt. Yeah? Yeah? Okay. Brought that guy over. Is equal to c m e to the m k t. Yeah? Now what do I want to do to solve for this? Yeah, factor out the x. So what do I have? 1 plus cx e to the m k t is equal to c m e to the m k t, and divide. No, there's no x, right? The whole point, we just factored the x out. Yes? Now we divide. So what is x? Explicitly, x as a function of t, divide by this guy, right? C m e to the m k t divided by 1 plus c e to the m k t. Okay, whew, that was a lot of work, right? That was lots of fun, lots and lots and lots of fun. That is one expression for the solution. It's actually a little bit nicer to not have all of these exponential guys in here, okay? And so now let's multiply by e to the minus mkt over e to the minus mkt, yeah? Why do we do that? Well, this gives us another solution, right? The beautiful thing that times that is just 1, right? That divided by that is the same thing. So I just get Cm, C is our arbitrary constant, M is our specific carrying capacity, divided by, well, again, this is, right, gotta multiply it across, e to the minus mkt plus what? These two guys together, C, that same arbitrary constant, yeah? And this is maybe a nicer way to look at it for a variety of reasons. Just there's less exponentials, okay? And since m and k are both positive right from the start, and if we took a limit as t went to infinity, tell me then what is the limit as t goes goes to infinity then of our function x of t? What's the limit as t goes to infinity of constants on top? That's nice, right? No L'Hopital's rule then, right? Constants on top, Cm, e to the minus mkt plus c, yeah? And where does this exponential decay term, because these guys are all positive, there's a minus, these are positive, t's not x, t's going to infinity. All right, careful with your letters. So where is this guy going? 0, that's exponential decay, right? Okay, so that guy's going to 0, so what are we left with? Cm over c, which is indeed m, yeah? And also helps you see why you couldn't just absorb the Cm into a new C. That wouldn't have given you, you've been mixing things up, okay? So that was a lot of work to go through. You know, it's obviously nice to have an explicit solution for lots of reasons. If you want to be able to predict the population at any particular time, right? You have a nice solution you can just plug in. But if you're only interested in the limiting value of the solution, what happens for a long time, then that would have been a ton of work to go through to discover that you're, you know, asymptotically what happens is that the populations go to M. We had that in 3 minutes, right? Maybe more, but on our little phase diagram at the very beginning. So there's a place for all of these different types of analyses and utilities with all differential equations, right? Okay, so before we close this guy up, I'll let you do a little fun, just algebra manipulations, and point out that we can come up with not only this nice explicit representation of the solution, but what if we had an initial value problem and we have this ODE and add the generic initial condition that x evaluated at t naught is x naught, right? Okay, x evaluated at t naught. So at some initial time t naught, the population is x naught, right? So that just means visually that t naught, x naught is on the curve, is on the solution curve, right? And so it doesn't have to, again, here's x and there's t, label your axes, and whatever it is, it doesn't have to be an initial value, it just has to be some value that you know, right? So, you know, maybe, you know, at this amount of, when this amount of time has passed, you know this amount of people, you know, are in the population, whatever it is you're modeling, right? That's the point, T naught, X naught, okay? So if you know that, right, then what can we do? We can determine C. And so I will leave it to you to show that with this initial condition, C can be shown to be X naught over M minus X naught, and therefore the solution of the initial value problem is, you should show for yourselves, is that x of t is x naught m divided by x naught plus m minus x naught e to the minus m k t. And then we've got this nice solution for any initial condition where we can discuss what's happening with the population in the logistic model. That's super fun, okay? So before we end, let me just mention one other problem that we've already done, but let's look at, take a 1.6 view on it. What if we did dx dt is x squared, okay? Or x prime is x squared. One of your homework problems, okay? Well, we've already done this, right? We did we did dy dx is y squared. Y prime is y squared. They're the exact same equation. We talked a lot about that. Okay? We solved that in a variety of different ways. We looked at it with phase plane analysis, but let's look at just like our phase diagram here. In this framework for our autonomous equation, okay, well, how many critical points are going to have? Just one, 0. Okay? X equals 0 is the only critical point. What do you know? X squared is always positive, so we're going away, right? Okay, increasing, solutions above are increasing, solutions below are increasing. Yeah? What type of critical point does that make this? Good. Semi-stable. Right? If you start below, if x starts negative, you go towards 0 as t goes to infinity, right? Remember, this is one little slice and everything is the same with t, yeah? Because there's no t on the right-hand side. But if you're a little bit away from 0 and positive, then what happens? You grow, right? Right? Solutions move away. You start a little off, solutions move back. You start a little off, solutions go far away. That's not good. Okay. So what do we know about this problem? What we did when we did this guy, we drew the representative solutions and phase portrait. We actually solved it with several differential equations, and we also mentioned that we saw blow up in finite time for this differential equation, which is again like not like a difficult looking equation. It looks innocuously simple, right? It's crazy. You can't see from this diagram that you would have blow up in finite time, right? You would just, see that as t went on to infinity, you would expect blow up, okay? And certainly if you looked at the concavity and you didn't see you had concave down, right? If you're increasing concave down, you may taper off. If you're increasing concave up, then you're in trouble, right? But the finite time, the fact that this will blow up, we looked at an initial value problem where, this blew up by the time you got to x equals 1. And so we didn't have to actually get the whole way out to infinity for things to blow up. And so that's kind of not going to come from this type of analysis. You're going to need more. But this type of analysis is super simple to be able to just quickly say what's happening with problems. Alrighty, that will be all for today. Go have some logistics fun, and I will see you for chapter 2.